Okay, good afternoon all. So in the last class, we looked at the first theorem, that is the class of regular languages is closed under union operation. So given two regular languages, the union of them also is a regular language. So to prove this, we took an indirect route. By definition, a language is regular language if it is accepted by some finite automaton or a finite state machine. So since we know the two input languages are regular, we know they should have their corresponding finite automata. So we took two finite automata. For example, we took two finite automata and then combined them to create a new automaton which accepts the union of these two languages. So since we are able to build an automaton which accepts the union of these two languages, the language recognized by this automaton is automatically a regular language by definition. So that's how we prove that the union of two regular languages is also a regular language. That is by constructing an automaton for that. Okay. So in the last class, we only discussed an example and the proof idea. We didn't prove it mathematically. So that's what we will do today. We didn't discuss the mathematical proof. We'll discuss that now. Okay. So let M1 recognize A1 where M1 is a 5 tuple Q1 sigma delta 1 small q1 and f1 and M2 recognize A2 where M2 is another 5 tuple Q2 sigma delta 2 small q2 and f2. Construct M3 to recognize A1 union A2 where M3 is again a 5 tuple Q3 sigma delta 3 small q3 and f3. Okay, so first let's define q3. So can anyone tell me what is q3 in terms of q1 and q2? What are the set of states? Yeah, it will be q1 cross q2. Why? If you remember, in this example, M1 has q1, q2, q3, M2 has r1, r2, r3. We should take every possible combination of one state from the first machine and one state from the second machine. So we get q1, r1, q1, r2, q1, r1, q1, r2, q1, r3, and again q2, r1, q2, r2, q3, r3, and so on. So for every state in the first machine, you build an ordered pair with every state in the second machine. So that is nothing but the cross product of q1 and q2. Okay. So q3 is nothing but q1 time or q1 cross product with q2, or another way of writing it is q3 is the set of all ordered pairs r1 comma r2 where r1 belongs to q1 and r2 belongs to q2. Okay. Then sigma is the same as in M1 and M2. In this theorem and all the subsequent theorems, we assume this for simplicity. Okay. The theorem remains true even if they have different alphabets, sigma 1 and sigma 2. Then we will modify the proof to let sigma 3 equal to, so what will be sigma 3 in terms of sigma 1 and 2? Yeah, union, sigma 1 union sigma 2. You just combine those alphabets to get sigma 3. So we just covered both the cases. In case they are different, then all we need to do is to do union. The proof, the rest of the proof remains same. But for simplicity, we will just assume in all the theorems that sigma is same for all the machines. Okay. Now, delta 3 is defined as follows. For each R1, R2 belonging to Q3 and each A belonging to sigma, let delta 3 R1, R2, comma A equal to, can anyone tell me? Yeah. Exactly. You see, in the resultant machine, basically what are the states? Each state is an ordered pair where the two elements in this ordered pair are coming from M1 and M2, right? So in this machine, you have states like each state is an ordered pair, Q1 R1, Q2 R2, Q2 R1, something like that, right? So in any finite state machine, given a particular state on a particular input, it goes to another state, right? So in this case, say Q1 R1 on 0, where does it go to? How are we deducing that? We take individual elements in this ordered pair, we take Q1 and sees where it goes to on 0 in M1. And then we take R1 and see where it goes to on 0 in M2, right? So basically what we are doing is say delta 3. So this Q1 R1 is actually an ordered pair, right? So Q1 R1, this is the entire state, comma 0. So how do I know what it is? I take delta 1 Q1 on 0, that is Q2. Okay, and then delta 2 R1 on 0, that is R1. Delta 2 R1 on 0, that is R1. So here the output will be again an ordered pair, Q2 comma R1. That, so it is mapping to Q2 R1, right? But this is a particular example. We already know the state names and all that. But while defining mathematically, we don't know the state names. So instead of writing Q2 R1, we write these things in the ordered pair. So in this ordered pair, first one is delta 1 Q1 0, and the second one is delta 2 R1 0. Okay, so that's what we are writing. So here delta 3 R1 R2 A will be an ordered pair with two elements, where first element comes from the first machine, second element comes from the second machine. So the first machine transition function is delta 1. So delta 1 R1 A. Okay, and second element comes from second machine, delta 2 R2 A. Okay, all right. What is the start state of the combined machine in terms of first two machines? Huh? Q1, Q2. You just combine the start state from the first machine and start state from the second machine, form an ordered pair. That will be the start state of the combined machine. Okay, and what will be the final states? Yeah, F1 cross F2. Right. So it is nothing but Q1 cross F2 union Q2 cross F1. Or another way of writing it is the set of ordered pairs R1, R2 such that R1 belongs to F1, and will you fill the remaining? R2 belongs to Q2. F2. Okay, R2 belongs to F2. What should I write here? R1 belongs to F1 or R2 belongs to F2. That's all. One of them needs to belong to the set of final states in the corresponding machine. Okay, that's all. We constructed a machine with all the features we need. So M3 accepts A1 union A2. Now suppose I modify F3 slightly. suppose F3 is set of all ordered pairs R1 R2 such that R1 belongs to F1 and R2 belongs to F2. Then can you tell me what M3 will accept? Yeah, exactly. M3 will accept intersection of A1 and A2. The slight difference. If M3 accepts only those strings which are accepted by either M1 or M2, it means it accepts union of A1 A2. If M3 accepts only those strings which are accepted by both M1 and M2, it means intersection of A1 A2, right? So instead of or, if it becomes and, it becomes intersection. That's all. So in that case, what will be the final state in this example? Yes, Q3 R2. There will be only one final state, Q3 R2. That's the only final state in the combined machine. Entire machine will be same, only the final state changes. That's it. Okay, then M3 accepts A1 intersection A2. Okay, so instead of or, if you put and, it changes. Okay, all right. Clear? Any doubts? Okay, all right. Now let's move on to the next theorem. Yep. It's a normal mathematical thing. I don't remember the full form. Yeah, coordinate demonstratum something, hence proved. That's what it means. It's a Latin term. It's regularly used in mathematical proofs at the end. Okay. The class of regular languages is closed under concatenation. That is RL1 dot RL2 is RL3. Okay. But proving this is not as simple as proving union. This is slightly complex. We can prove using previous kind of method, but it's more complex. To make it simpler, we need to introduce a new concept. Can anyone guess what the new concept is? Huh? Sorry, I didn't get. Yes. Yes, non-determinism. So we need to introduce non-determinism to prove this theorem. Okay. Okay, so let's just take an example of a non-deterministic machine. Okay, so Q Q4. Q4 is the final state. Okay, so this is an example of a non-deterministic finite automaton. Do you notice any differences between this and a deterministic finite automaton? Okay, there is epsilon. Yeah. Finite accepts. Exactly. There are multiple outgoing arrows for the same input symbol. There is more than one outgoing arrow for the same input symbol. But in a DFA, there is exactly one outgoing arrow for each symbol. There can't be less, there can't be more. For each state, for each input symbol, there has to be exactly one outgoing arrow. But in an NFA, there can be 0 or 1 or more outgoing arrows for any input symbol for any given state. Okay? Any other differences? Yes, same thing. Like here, Q1 on 1, it goes to both Q1 and Q2. All right. So this also tells us about the difference in the nature of outputs of DFA and NFA. In a DFA, what is the output for a given input state and input symbol? No, just for a particular symbol, for a particular state, some state is the output. Okay. But here, what is the output for a given state and a given symbol? Exactly. It is some set of states. Okay. It is not just one state. Like if you take this, suppose delta Q1 comma 1. Now there are two states, Q1 and Q2, but I can't write it as just like this. These sound like two outputs, but a function can't have two outputs. You need to combine them into one unit. So you need to put them in a container, that is the set. So here the output is a set of states. In an NFA, the output for a given state and an input pair is always a set of states. Whereas in a DFA, the output is just one state. So you don't need the concept of set there. Okay. So this is another difference between NFA and DFA. So three main differences. One is for a given input, there can be 0 outgoing arrows. Like here you see in Q2, there is no outgoing arrow for 1. In Q1, there is more than one outgoing arrow for 1. In Q3, there is only one outgoing arrow for 1. So for a given symbol, you can have 0 outgoing arrows or one outgoing arrow or more than one outgoing arrows. Any number of outgoing arrows, it doesn't matter. That is one main difference. The second thing is here, epsilon is also allowed as a transition symbol. So what does epsilon mean here? It means if you enter Q2, then either on reading 0, you can go to Q3, or even on not reading any input, you can go to Q3. So if you have come to Q2, then you have also automatically reached Q3 without reading any input. So you got Q3 for free if you get Q2. That is one path. Another path is if you get 0, then also you go to Q3. That's a different path. So it's taking more than one path. Similarly, if you are in Q1, if you get a 1, you either go to Q1 or you go to Q2. So these are two different paths. If you go along this path, you will reach somewhere. If you go along this path, you will reach somewhere. So these are alternate paths that the machine is simulating. These are parallel paths the machine is simulating. We will look at that in a while. Yeah. Yeah. So whatever arrows are not visible here, you can assume they are going to some dead state. You don't need to explicitly mention the dead state in an NFA. because for all the symbols where there are no arrows, like in Q2, there is no outgoing arrow for 1. So you can imagine some dead state and Q2 on 1 goes to dead state. Similarly, Q3, there is no outgoing arrow for 0. You can imagine that goes to dead state. So whatever is not indicated here, implicitly, it goes to dead state. You don't need to explicitly mention here. But you can imagine, basically, when you try to convert it to a DFA, you need a dead state. But here you don't need. Okay, every DFA need not have dead state. Even in DFA, you need to have dead state if the regular states don't do the job. Okay, in this case, we need not mention all the states. It is assumed whatever are not visible, they are going to dead state. Okay, yeah.
What will happen if we input 1 to Q2?
Nothing will happen. It will just halt the machine. If we input 1 to Q2, it will get stuck. It doesn't know what to do. It goes to dead state. That's it. It ends there. It will not even read the next symbol. That's all. We'll see. We'll look at one example just in a few minutes. But before that, let me write the distinctions between a deterministic finite automaton and non-deterministic one. Yes, that's what I'm going to write later. Okay, so in a DFA, every state has exactly one exiting transition arrow for each symbol in the alphabet. In an NFA, a state may have 0, 1, or many exiting arrows for each symbol. For each alphabet symbol. In a DFA, labels on the transitions are from the alphabet. What about NFA? In a DFA, the labels on the transitions come only from the alphabet. What about NFA? Yeah, so the labels can come from the alphabet or epsilon as well. But epsilon still is not a member of the alphabet. Epsilon is separate. It is allowed as a separate symbol, but still it is allowed. Okay, epsilon can never be a member of sigma, as we discussed earlier. Okay. An NFA may have arrows labeled with members of the alphabet or epsilon, that is sigma union epsilon. Okay, 0, 1 or many arrows may exit from each state with the label epsilon. And the last difference, in a DFA, the transition function takes a state and an input symbol and produces the next state. In an NFA, the transition function takes a state and an input symbol or empty string and produces, what does it produce? What is the difference? Yeah. Yeah. And produces the set of possible next states. The important thing is it's a set. Okay. In DFA, it is one state, whereas in NFA, it is a set of states. All right. Okay. So is clear? Okay. Now let's discuss some advantages of NFA. Every NFA can be converted into an equivalent DFA. Constructing NFA is easier than directly constructing DFA. So if you find it difficult to build a DFA, what you can do, you can first construct an NFA and then convert it to DFA. All right, every NFA can be converted to DFA. NFA is much smaller than its deterministic counterpart. And DFA quite often has more states than its equivalent NFA. So another way of understanding non-determinism, so coming back to non-determinism, it is a generalization of determinism. It can be viewed as parallel computation. Okay, so basically you can imagine like when there are more than one outgoing arrows for a particular symbol, you can imagine it as parallel computation. So it can take either this branch or some other branch. So once it takes a particular branch, it goes forward in that branch and it takes one path. All right. So you are simulating multiple paths at the same time. So for the same input, it can go in multiple paths. So you are simulating all those paths parallelly, right? You're not waiting for trying out one path, then another path, then another path. You're not doing that. You're trying out all the paths parallelly where it can go for a given input symbol. Okay, so this is like having multiple threads at the same time, right? So it makes our job easier, both in terms of constructing the machine and also in case you actually want to simulate it on a parallel computer, it will do the job faster. Okay, so that's a simple way of understanding non-deterministic computation. But technically, NFA is no more powerful than a DFA. Both are equally powerful. The only thing is NFA is more convenient than a DFA. That's all. This is true only for finite automata. But when you go to pushdown automata, there is a difference between non-deterministic pushdown automata and deterministic pushdown automata. There, non-deterministic version is more powerful than the deterministic version. But here, non-deterministic version and deterministic versions are equally powerful. Only difference is convenience. Okay. So let's yeah. So if at least one of the branches of the NFA process tree is in an accept state, by the time it is done reading the input string, the input string is said to be accepted by the NFA. And in turn by its equivalent DFA. So again, like I said, you are given an input string and you are reading one symbol at a time. So in a particular state, when you read a particular symbol, you can take more than one branch. So you will simulate all these branches. Some of these branches will go till the end. Some of these branches will be discarded in between because you are stuck. You don't have the transition for that particular symbol on that particular state. So those branches will be discarded. At the end, when you are done reading the input string, there may be multiple branches. In any of these branches, the leaves, if at least one of these leaves is a final state or an accept state, then the string is said to be accepted by at least one branch, which means it is accepted by the machine, the NFA, which means it will be accepted by its equivalent DFA. Okay, so we'll look at an example now. So let's take this same machine. But let me use the next page. So let's call this N1. Okay, and let us run N1 on input string 010110 to get the process tree. Okay, so let's say Q1, this is the start state, and then we keep reading the input symbol. So first symbol is 0, right? So Q1 on 0, where does it go to? Just Q1. Okay, so Q1 on 0, it goes to Q1. And then next symbol is 1. Okay, so on 1, Q1 goes to Q1 and Q2. All right, but Q2 also has an epsilon transition with Q3. So the moment you reach Q2, you can also reach Q3 without reading any more symbol. So the moment you read 1, you can reach Q1, Q2, and also Q3. Okay, so all those three will be listed at the same level. Okay. So Q1, Q2, Q3. All right. Now next symbol is 0. Now for each of these states, you should see where it goes to on 0. Q1 on 0 goes to Q1. Q2 on 0 goes to Q3. Q3 on 0 goes nowhere. So that branch is gone. You can't proceed further in the Q3 branch. So only Q1 and Q2 branches are left. Q1 on 0 goes to Q1. Q2 on 0 goes to Q3. So Q1, Q3. So Q1 on 0 goes to Q1. Q2 on 0 goes to Q3. Q3 on 0 doesn't go anywhere. So we can say it is dead. That branch is dead. All right. Now next symbol is 1. All right. So next symbol is 1. Now where does Q1 and Q3? Yeah. Yeah. So Q1 on 1 goes to Q1 and Q2. But whenever you get Q2, you will get Q3 with it freely. So you always assume Q2 and Q3 are like a set. Q2 will not come alone. Q2 will bring Q3 with it. So it's going to Q1 and Q2 and Q3 at the same time. All right. And Q2 on 1 goes nowhere. Sorry, not Q2. It is Q3. Q3 on 1 goes to Q4. Okay. So Q1 goes to Q1, Q2, and Q3 comes freely along with Q2. Q3 goes to Q4. All right. Okay. Now, next symbol is again 1. Okay. Q1 goes to Q1, Q2, Q3. Q3 does not go anywhere on 1. So Q2 branch is gone. That will die out. Q3 goes to Q4. Okay. So Q1 again goes to Q1, Q2, Q3. This branch dies out. There is no output defined for Q2 and 1. And Q3 goes to Q4. This Q4 also we should see Q4 on 1 goes to Q4. Okay, so this Q4 goes to Q4. All right. Now next symbol is 0. Q1 on 0 goes to Q1. Q2 on 0 goes to Q3. Q3 on 0 goes nowhere. Q4 on 0 goes to Q4. Yeah.
We are at Q1, we got 1, so we go to Q2. Then if we get 1, we'll stay at Q2. How will we go to Q3?
I didn't get. Like here on Q1, I got a 1. I went to Q1 and Q2. because arrow is there, no? Q1 goes on one, Q1 and Q2. It takes two paths. So Q1 goes to Q1 or Q2 on one. But without reading any more symbol, it can go to Q3 also because it reached Q2.
But if the next step symbol is there one, so it should stop at Q2.
Yes, if the next symbol is 1, it will stop at Q2. So where did I write? So here you see Q2 and then 1. It stopped, no? I didn't go further. Okay? Yeah. So Q1 on 0 goes to Q1. Q2 on 0 goes to Q3. Q3 on 0 is dead end. Okay, Q2 on 0 goes to Q3. Q3 on 0 goes nowhere. Q4 on 0 goes to Q4. Again, this Q4 on 0 goes to Q4. All right. Now, all you need to see is we are done. We are done reading the string 0, 1, 0, 1, 1, 0. Right? This was the string 0, 1, 0, 1, 1, 0. So that's the string. We read all the symbols 0, 1, 0, 1, 1, 0. We are done. Now, these are the leaves of the tree. Okay. All that we need to do is we need to check, are there any final states here? Yes, there are final states. So two branches in this process tree are ending in final states. Even if one branch ends in final state, it is fine. Okay. So 0, 1, 0, 1, 1, 0 will be accepted by N1. Okay. So only states at this final level matter. Nothing else. All right. At this final level, if there is at least one accept state, the string will be accepted. If none of these leaves have a final state, then the string will not be accepted. All right. Simple. Okay. Let's stop here.